All right, folks, so I am on page 12 in your packet with logistic functions. If you don't have it handy, you're going to want to pause the video for a minute and grab your calculator because we are going to be doing some calculating. And then let's get ready to do some logistic functions. All right, I want to start for a minute by remembering our friend the exponential function. And I'm going to say you might not want to graph this quite yet because I'm actually going to do some modifications to my exponential function. So typically if I wanted to use an exponential function to model something like growth, my exponential function would look like that. And if I wanted to use my exponential function to model something like the growth of rabbits or deer per se, and if I looked at that exponential function, it would give the indication that that deer or rabbit population was going to grow indefinitely. But we all know that that rabbit or deer population is going to be limited by factors such as the environment, how much room there is to maybe have places for the deer to live. It might be affected by how much food the deer or the rabbit have to eat. So expecting that population to continue to grow forever and ever might be somewhat unrealistic. So we're going to take and we're going to modify that growth just a little bit. And at some point, that population is going to max out due to constraints like the availability of places for the population to live, the availability of the uh, population to have things to eat. And again, that population will start to level out. And what happens when that population starts to level out is we end up with a function that rather than exponential in nature is now what we call logistic in nature. So it ends up being kind of an S-shaped curve. Like the exponential function, the logistic function also has a horizontal asymptote at y equals 0. It also has a second horizontal asymptote whose equation is going to be y equals c, where c is the numerator of the function that we just graphed. So two horizontal asymptotes, one at y equals 0, one at y equals c. And you'll notice that this function is bounded, right? The graph is totally contained in between those two horizontal asymptotes. And I'm looking briefly at the two different formats in which you might see this logistic function come at you. The first one says it might be in some form f of x equals c, the upper horizontal asymptote, over 1 plus a times b to the x. The second one is a little funky looking. If I look at that denominator, we haven't looked a whole lot this year at the irrational number e. And we'll do more with e after the first of the year, but for now you need to know that that number is an irrational number, kind of like pi is an irrational number, and it's approximately equal to about 2.7. And again, we'll talk more about E after the first of the year, but that's for what you enough for what you need to know right now. The other thing that you need to know here is that C, the numerator of the fraction, represents either what we call a growth limit or a carrying capacity. It is the value that the population will approach but never quite reach. And because the curve approaches that number but never quite reaches it, the maximum population is going to be one less than that number. So I'm going to say C subtract 1. All right, so there's your equation for the logistic function, a little bit about what it's used for and used to model. We're going to go in and look at some attributes of the graphs and attributes of the equations and then use it to actually do some modeling. All right, so directions here say to graph the function. We're not going to do that. Rather, we're going to just go find the y-intercepts and the horizontal asymptotes of each of these functions. I'm going to go ahead and jump right into number 1, and I'm going to jump into the horizontal asymptote piece because that's easier. So the horizontal asymptotes will always be y equals 0, the x-axis, and y equals the numerator. So in this case, y equals 8. And then I'm going to go find the y-intercept, and I'm going to go find the y-intercept the same way I've been doing dozens of times all year. I'm going to remind you that we find that by replacing x with 0. And I can do that very nicely without a calculator because I'm going to remind myself that any number to the power of 0 is always 1. So when I start in that denominator, I'm going to start with a 0.7 to the 0 power. That gives me a 1. 3 times 1 is 3, plus 1 is 4. And 8 over 4 is 2, making my y-intercept 0, 2. All right, I'm going to leave 2 and 3 for you and move on to number 4. In number 4, again, I'm going to find the asymptotes first. So our horizontal asymptote on the x-axis at y equals 0. And a second that's the same as the numerator of that fraction, y equals 800. To find the y-intercept, again, I'm going to replace x with 0. So 800 over 1 plus 7 times e raised to the power of negative 0. I'm going to evaluate exponents first. So e to the power of negative 0 becomes 1. 7 times 1 in the denominator is 7, plus 1 more is 8 for my new denominator. And 800 divided by 8 leaves me at 100. So my y-intercept then would have coordinates 0, 100. All right, so again, there's a little bit on the logistic function, its graph, and its attributes. Up at the top of page 13, where I'm at right now, we're actually going to go look at some applications of the logistic function. So it tells us that this function b represents a population of rabbits. And for this population in rabbits, t represents time in months. It wants to know, according to this model, what was the initial size. I'm going to tell you that the initial size occurs at time 0, or when the time is equal to 0. So I'm going to start by evaluating b of 0, or in other words, replacing each t with a 0. So doing that would give me a 250 in the numerator. In the denominator, I've got 1 plus 4 times e raised to the power of negative 0 divided by 4. Exponents first. 0 divided by 4 is 0. E to the 0 is 1. So this becomes 250 over 1 plus 4 times 1, or 250 over 5, making my initial bunny population 50. The second piece of this wants to know after how many months. So in other words, what is the t-value going to be equal to when the population has doubled in size? Well, if the population started at 50 and is doubled in size, that makes the new population equal to 100. So we want 100 to be equal to our fraction 250 over 1 plus 4e to the power of negative t over 4. We're actually going to talk about some algebraic solutions of these types of equations after the first of the year, but for now, to keep things simple, we're going to solve this on our graphing calculator. And the way that we're going to solve this on our graphing calculator is that we're going to look at each side of this equation independently. We're going to look at y equals 100, and we're going to look at y equals 250 over 1 plus 4e to the negative t over 4. So this is where you're going to, if you need to, pause the video and go grab your graphing calculator so we can do some graphing. I've got my calculator handy. I'm going to go in and add a graph. And again, if you need to, pause until you've got yours handy and ready to go. The two functions we wanted to graph were y equals 100. And then to add the second graph, I'm going to Control G. The second graph is considerably more complex. The e on your calculator is going to be over here on the left side. And we want to do e to the power of negative t. So I'm going to do negative x over 4. I know that this graph has a horizontal asymptote at y equals 250. So that's going to help a little bit with my window. I might make my window go from negative 10 to like 300. And the x values, I'm just going to play some games and see what happens if I go from, well, that was a pretty good guess right off the bat, going from 0 to 100. But I really want to focus in on that portion of the graph where things crisscross. So I'm going to go and reset my window. And maybe I want to go negative 1 to, I don't know, 20. Oh, that's a much better window. Perfect. Since I want those two values, the red graph and the blue graph, to be equal, or I want to know where those two are equal, I'm going to go in and analyze the graph for the point of intersection. So choice 4. And it looks like those guys intersect at the point whose coordinates are 3.92, comma 100. So these fellas intersect at the point with coordinates 3.92, 100. Notice that they do not specify what I should round to here, so I'm just going to be a little clever and creative in my answering of this question. It wants to know after how many months. I'm going to say about or approximately 4 months. Now you could say after about 3.9 months and be absolutely every bit as correct. You could say after about 3.92 months and be just as correct. But I'm going to say about 4 months because people don't typically talk or speak in 3.92 or 3.9 months. All right, and then to wrap this question up, Part C wants to know the largest possible population of rabbits. Well, again, we have that horizontal asymptote at y equals 250, so we know that our population will approach but never quite reach 250. So the largest possible population will be one less than that, or 249 rabbits. All right, at this point, I'm going to go ahead and flip up to the top of the next page. And on this page, they're going to ask us to compare the graphs of exponential growth, decay, in logistic. And in the interest of time, so you don't have to listen to me babble forever, I'm just going to sketch these for you. So the first graph is an exponential graph. Due to the fact that our base is a number between 0 and 1, this is exponential decay. So that graph is going to look as such. The second graph has a base of e, so a number greater than 1, which is going to make that second graph growth. And the last graph is our new logistic friend with that nice S shape. Our graph which looks something like that. And again, in the interest of time, so that you don't have to listen to me prattle onwards, I'm going to leave the rest of that for you to figure out. And I'm going to boogie on to page 15. I'm going to make every attempt to get this video done in the next 5 minutes or so. All right, so this will be the last question that we talk about together. It too has to do with population, but then rather than rabbit or deer population, this we've got to take a look at human population. And it talks about human population in New York State back in the 19th century. It gives us an equation that models that population. One thing that's worthy of paying attention to here is that P represents the population in millions, where T represents the time in years. And it would be the time since January 1st of 1800. It says, based on this model, what is the population in New York State in the year 1850? Or in other words, 50 years since the year 1800, making our t value equal to 50. So I'm going to go ahead and evaluate P of t, and that's going to be the 19.875 value over that long denominator of 1 plus the 57.993 times e raised to the power of negative 0.035005 times 50. And this I'm not even going to try to do without the use of a calculator. So I'm headed back to my calculator here. I'm going to go open up a new document. This time I actually want to do some calculating. And I've got this nice fraction where I have the 19.875 number in the numerator. And again, my E value, or my E button, is over on the left side. And I end up with about 1.79455. And again, they don't tell me what to round to here. So I'm going to say about 1.8. And again, that population is in millions. But again, notice my use of the word about or approximately. Letter B wants to know what will be New York State's population in the year 2020. I'm going to leave that for you to determine. The maximum sustainable population is going to be 1 less than the numerator. So it appears as though that numerator is about 19.875 million, or in other words, 19,875,000. So again, that is the number which the graph will approach but never quite reach. The maximum sustainable population is one less than that. 1,874,999. And then it wants to know during what year will the population reach 1 million people. In other words, we've got 1 equals the 19.875 over, and this 2 is going to be another graphing calculator question. I'm going to graph those two different functions. I'm going to graph y equals 1. I'm going to graph the y equals 19.875. I'm going to play some games with my window until I get a nice viewing window where I can adequately see both of those graphs and their points of intersection. And that'll steer me towards my answer. So I'm going to leave that for you to finish up. I'm going to tell you that your homework for over the weekend, which I am desperately hoping that you can get done in class, is to finish all problems. From the first page of this section on page 12 to the last page, which is 16. Have a wonderful weekend, and I anticipate seeing you on Monday. All right, take care for now till Monday. Thanks for bearing with me, folks. Bye now.